All right, welcome back, everyone. Today, we're diving straight into the absolute core foundations of data systems. If you've ever built a backend or, just sketched out a system design and wondered, how do the biggest apps in the world actually manage all their data? Well, you are definitely in the right place. We're going to break down the massive architectural split that pretty much defines every modern data-intensive application. Okay, let's dive right into this because honestly, it's a question practically every engineer asks when they first start out. Like, why can't one database just do it all? Why can't we just spin up a single massive, super powerful database, cross our fingers, and let it handle literally every workload we throw at it? I mean, it seems like it'd make our lives so much easier, right? But treating databases as this one-size-fits-all magic box, yeah, that's a rookie assumption, and it falls apart really quickly in the real world.
So here's our roadmap for today's explainer. We're going to cover the two data worlds, OLTP systems, OLAP systems, the access pattern clash, a real-world e-commerce system design, and finally, choosing the right storage. Let's go.
Section 1, the two data worlds and the myth of the universal database. Look, when your app is small, maybe a side project, you can absolutely get away with a single database doing everything. But the second you start scaling users and complexity, that unified approach just completely hits a wall. The reality is different workloads demand entirely different system designs. And here's the kicker. Raw CPU power isn't really the bottleneck anymore. We have super fast processors. The real beasts you have to wrestle with are data volume, complexity, and most importantly, your access patterns. Basically, how is your application actually reading and writing the data? A system that's perfectly tuned for one type of data access is literally going to choke if you force it to do the exact opposite. Moving to Section 2, OLTP, which stands for Online Transaction Processing, the Agile Frontline Worker. I want you to picture an OLTP system like an incredibly fast frontline cashier at a super busy grocery store. They're handling rapid individual requests, one right after the other, making sure nobody has to wait in line. By definition, these systems are absolutely optimized for fast, interactive, user-facing requests and very low latency updates. Think about it. Whenever a user clicks a button, drops a comment, adds some sneakers to their cart, boom, that's a transaction. These databases represent the absolute, real-time, current state of your app. If a user updates their email, the OLTP system processes that instantly. So the crucial point here is that OLTP is all about keeping your application snappy for the user. The workload is highly specific. You're looking at a constant barrage of tiny reads and writes that demand incredibly low latency because, well, an actual human being is sitting there staring at a loading screen. It performs frequent random access updates, and usually it finds data by looking up a very small number of records using an index, kind of like instantly finding a specific user ID out of millions. Fast, precise, and targeted. All right, let's shift gears completely for Section 3, OLAP, or Online Analytical Processing, the strategic backend thinker. If OLTP is that fast-moving frontline cashier, OLAP is essentially your strategic manager sitting in the back office looking at the big picture. These systems honestly don't care about a single transaction happening right this second. Instead, they're designed to scan and aggregate massive volumes of historical data to generate business intelligence. They aren't serving an end user clicking around your website, they're serving internal business analysts. They hold this vast, sweeping history of everything that's ever happened in the system over time, rather than just what's happening right now. Because of this, the workload characteristics for OLAP are literally the polar opposite of OLTP. An analyst might fire off a query that needs to scan millions or even billions of records at once. They're calculating aggregations, sums, counts, averages, stuff like, hey, exactly how many users in Europe bought our premium subscription last November? To figure that out, the system has to chew through terabytes, or honestly, even petabytes of historical data. And notice, these queries are almost entirely read-only. Actually, if you tried running one of these massive queries directly on your live OLTP database, yeah, you'd probably crash your live website. Not a great day for an engineer. Which brings us to Section 4, the access pattern clash, and why these two systems inherently fight. This fundamental clash in access patterns is exactly why the myth of the universal database just falls apart. It all boils down to point lookups versus bulk scans. For an OLTP point lookup, you want to find one specific user's data instantly, right? So engineers use indexes, very much like the index at the back of a textbook. It points the database directly to the exact spot on the hard drive. Boom, done. But if you need to do an OLAP bulk scan, like calculating the average age of 10 million users, that index is suddenly entirely useless.
You don't need a tiny pointer to one record, you need to literally rip 10 million records off the hard drive as fast as physically possible. And this brilliantly illustrates the real physical divide here. Look at this breakdown. Because OLTP relies on jumping around the disk to find individual records, its main bottleneck is disk seek time, literally the time it takes the hardware to physically find the data. But OLAP, it's streaming massive amounts of data sequentially, so its main bottleneck is disk bandwidth, basically how fast can we shove data from the disk into memory. You simply cannot perfectly optimize one single storage engine to conquer both seek time and bandwidth at the same time. It's an engineering trade-off. Let's look at Section 5. E-commerce system design and the data journey. Let's make this super concrete. Imagine a user clicks buy on an online store. Step 1 happens in the OLTP database. It instantly creates the order, processes the credit card, and drops the inventory count so the item doesn't get double sold. Fast, low latency, happy customer. Then we hit Step 2, a process called ETL, that stands for extract, transform, and load. Behind the scenes, the system periodically extracts a copy of that new order data from the live OLTP database, cleans it up, and loads it into an entirely separate data warehouse. Finally, in Step 3, that back-end OLAP data warehouse stores the historical record. Now, an analyst can run a massive, complex revenue report at the end of the month without ever slowing down the live customer-facing checkout process. It's a beautiful separation of concerns. Moving to Section 6, choosing the right storage. Row versus column. Now, what's really interesting about this slide is how these specific access patterns literally dictate how we store data on the physical hard drive. Traditional OLTP databases use row-oriented storage. That means all the data for one specific user, like their ID, name, email, and home address, is stored physically contiguous, right next to each other on the disk. This makes pulling up a single user's complete profile incredibly fast. But OLAP systems? They use a secret weapon, column-oriented storage. In this layout, all the values for a single field, let's say just the purchase amounts for every single user, are stored together. So why is column storage such a massive game changer for analytics? Well, think about it. If an analyst only wants to sum up total revenue, a traditional row-oriented database forces the system to load every single entire record into memory. We're talking names, addresses, phone numbers, all just to pull out that one revenue number. It's a colossal waste of disk bandwidth. Column storage, however, allows the system to completely skip all that irrelevant data. It just grabs the revenue column. Plus, because a column contains identical data types, like thousands of integers right next to each other, it can be tightly compressed. This minimizes disk reads even further and perfectly solves that exact bandwidth bottleneck that OLAP systems face. It's super clever. So, as database technologies keep evolving, we are starting to see emerging systems that attempt to bridge this gap, offering sort of hybrid approaches. But the raw physical constraints of hardware and access patterns, those remain deeply, deeply entrenched. So what does this all mean? Will the industry ever find a way to seamlessly merge transaction processing and analytics into one perfect box? Or is this fundamental divide just a permanent fixture of software engineering? It's a fascinating question to chew on the next time you're architecting a system. Thank you so much for joining me for this explainer. Keep learning, keep building, and definitely take a closer look at how your own applications balance these two fundamental worlds. Catch you next time.